Let's look at a simple home experiment. Two identical objects, and one plastic ruler placed between them and the observer. Here, light bends downward, and the object behind the ruler appears lower than it actually is. When we remove the refractive element, both objects align perfectly. No illusions, just straight-line vision. But when the ruler is moved below the object, light bends upward, and now the object appears higher than it really is. These are the two faces of refraction, the lifting effect and the lowering effect. This is not interpretation, this is physics. And if such an effect happens with a piece of plastic on your kitchen table, imagine what can happen with an atmosphere that refracts across hundreds of kilometers. What determines the path light follows? At first glance, the answer seems obvious, from source to observer, in a straight line. But nature works differently. It doesn't choose the shortest distance. It chooses the fastest route. When light moves through different media, like from air into water, its path changes. It bends because light travels at different speeds in different materials. Faster in air, slower in water, and to reach its destination in the least amount of time, light chooses a different route than we might expect. It doesn't come straight. It doesn't come direct. It comes in a way that obeys the law of time minimization. This law is known as Fermat's principle, and it's one of the most powerful algorithms in nature. It explains why light changes direction and why that change always makes perfect physical sense. This principle applies not only between two media, it applies even where the medium itself changes, like our atmosphere. At first glance, this green line looks correct. It's the shortest. It seems logical, but it's not the fastest. Light takes a different route, curved but efficient. It spends more time in the faster part of the medium and only later crosses into the slower layer. But the key is, where does the light hit? The straight geometric path, the green line, would hit lower. But the real light path, due to refraction, hits higher. That's why the sensor records the light at a point different from where we intuitively expect. Atmospheric refraction illusions. So far, everything was simple. Water, glass, a ruler. Refraction, clear and visible. But the atmosphere, it seems invisible. Yet in truth, it's powerful. Our senses can't see the refraction between layers of air. But light can. And it silently adjusts its path, millimeter by millimeter. As we ascend in the atmosphere, air density decreases exponentially. As a result, the refractive index of light also decreases with height. According to the Gladstone-Dale relation, the refractive index depends on air density, 1 plus A constant times the density. Expressing the density with an exponential formula, the derivative becomes minus K times the sea level density, divided by the scale height, multiplied by the exponential term. Plugging in the values, Kday equals 2.9 times 10 to the minus 4, Ya0 equals 1.225, H equals 8,000. We get the vertical refractive index gradient is minus 1.6 times 10 to the power of minus 7. This explains why light bends slightly in the atmosphere. Fermat's differential equation. Using Fermat's principle and our gradient, we compute the real light trajectory through the atmosphere. This curve is mathematical, not illustrative. It says if the refractive index changes, the light path curves. When there is no refraction, without refraction, light travels in a straight line. The sensor records the shortest path. This is vision governed by geometry, without bending. When refraction takes over, in the atmosphere, the refractive index increases closer to the ground. Light begins to bend downward. Only one trajectory, the fastest, reaches the sensor, and that is the one recorded. The point of perception shifts. Reality changes. What gets hidden? If light bends down by 8 centimeters over 1 kilometer, then an object 1 kilometer away and 8 centimeters tall becomes completely invisible to an observer positioned at 0 kilometer elevation. If it's 9 centimeters tall, we only see 1 centimeter above the horizon. The rest is lost. This only holds true because the observer is located at ground level. Had the observer been elevated by even 1 centimeter or 1 meter, the visibility would change significantly. This is not because of Earth's curvature. It's pure optical physics. Conclusions and teaser. The visibility of distant objects doesn't depend on Earth's shape or height. It depends on whether light from them can reach our sensor. The farther the object, the more of it disappears. And that disappearance is exponential. In the next episode, we'll look at real-world examples: wind turbines disappearing at sea, Chicago skyscrapers floating over Lake Michigan, and the sun lingering above the horizon longer than geometry allows. All of it explained not through illusions but through the laws of light's path. In conclusion, atmospheric refraction affects what we see, and that is a physical fact. Due to refraction, light bends downward, away from its purely geometric path. For example, over 1 kilometer, the deviation is about 8 centimeters. Over 2 kilometers, the deviation is about 31 centimeters. Over 5 kilometers, the deviation is about 2 meters. And this bending grows exponentially. This effect can be precisely calculated using a refractive gradient of 1.6 times 10 to the power of -7 and Fermat's second-order differential equation. It's not an illusion. It's how light behaves physically. Is that a lot or a little? That's for you to decide. But the idea that refraction has no effect on what we see is simply absurd when the math says otherwise. And this optical change must be accounted for, whether we stand on a flat or a curved surface. The path of light depends on refraction, and that truth does not disappear.